So we're going to begin by looking at how we can go through the process of multiplying polynomials and focusing on our key questions. First, how can we use the area model to help us as we need to multiply polynomials? Can we follow that up and see about using an area model to also do an inverse operation, so the opposite of multiplying, which would be dividing? We're just going to kind of introduce that idea. And then finally, how do we apply these ideas to either contextual or problems or problems that give us a diagram or a picture? How can we also multiply in those situations? So, as a quick reminder, we want to see how multiplying with the area model can assist us and give us some help and support in making sense of multiplying polynomials. But I want to remind you of how this area model was taught to you when you were younger. So the problem here, 14 in parentheses beside 23 in parentheses, that's the same thing as 14 times 23, right? It just means we're multiplying. And there's different ways you can do this. There's a traditional algorithm where you line them up over top of one another. This is the way most of your parents would probably remember how to multiply. And then you work through and multiply digit by digit, starting with the ones place on the bottom term, 3 times 4 being 12, 2 times 4 being 8, but then you use that carried 1 to make a 9. And then we go over one digit to the tens place. The 1 times the 3 is 3, and then the 1 times the 2 above that is a 2. And then we add our digits vertically. So 2 plus nothing is 2, 9 plus 3 is 12, carry the 1. We end up with 322. So that's the traditional way. But you were probably also taught how to draw an area model for this. And you split your values into smaller parts. For example, the 14 could be thought of as 10 plus 4, and the 23 as a 20 plus a 3. So let's see if we multiply this out, what the areas inside of this area model become. So the area in the top left has a height of 10 and a width of 20. 10 times 20 makes 200 for that area. 10 times 3 makes 30 for the top right. 20 times 4 makes 80. And 4 times 3 makes 12. And then to finish this problem, we find the total area by just adding these values up. Okay, 200 plus 30, that makes 230. 230 plus an 80, that makes 310. And 310 plus the final 12 makes a total of 322. And I was just doing those sort of adding on one value at a time. You could have obviously written them all out and added them together all at one step, but I like to break it up to keep track of the numbers in my mind. But we see we get the exact same number. And we can also start to kind of see where these values show up in the traditional model too, right? The 80 and the 12 makes 92 together. Well, that's what number showed up here. And then the 20 and the 30, or excuse me, 230, that is what's actually taking place here. If we were to put a 0 as a placeholder, there's the 230. So we can see the numbers are the same. Now, the reason that they started teaching that model to kids for how to break up areas or break up multiplication problems is actually to benefit us now that we're in more advanced math. Because here we have two terms, 3x plus 4, times a trinomial with three terms, x squared minus 5x plus 6. And to multiply this, we can use an area model that has two parts or 2 rows tall and 3 columns wide. So we'll put a 3x and our plus 4 in front. And then we'll put x squared minus 5x and 6 across the top. And now we multiply just like we did before. 3x times x squared. Well, that x squared is 1x squared. And since 3 times 1 is just 3, that stays our coefficient. X squared times another x gives us 3 factors of x, or x cubed. So notice that when we multiply variables times variables, those exponents increase because we now have more x's being multiplied together. Then in the middle on the top, 3 times negative 5 is negative 15, and x times x is x squared. And then for the top right, 3 times 6 is 18. The 3 had an x, but the 6 did not, so we still just have one factor of x altogether. Now we move to the bottom row. 4 times 1x squared is 4x squared. Notice here, since the 4 is a constant, that's just going to be changing the coefficients, but we're not bringing any more x's into this product. 4 times negative 5 is negative 20. And then we still have the x from the top. And our constant in the bottom right, 4 times 6, that makes 24. And now our sort of final step of this is we need to combine any like terms and list out the product. So if I write this whole thing as it is, 3x cubed minus 15x squared plus 18x, then I have plus 4x squared on the bottom row, a minus 20x, and a plus 24. So what I want to do is identify any like terms. I only have one x cubed term, so I want to write that down here, 3x cubed. X squareds show up here and here. I have negative 15 or minus 15x squared and a plus 4x squared. Since I have some minuses and some pluses, those are going to cancel each other out a little bit. If you do 15 take away 4, that's 11. And because we had more negatives, that means it's a minus or a negative 11x squared. Then as far as x's go, I have 18 minus 20. That leaves me at negative 2 or minus 2x. And I end up with a constant, only one of those, which is plus 24. So the product, when I multiplied 3x plus 4 times x squared minus 5x plus 6, is 3x cubed minus 11x squared minus 2x plus 24. Let's move to our next practice problem. Same idea. Can we still use the area model to help here? Absolutely. We have two terms, 2x minus 1, being multiplied by three terms, x squared plus 3x minus 2. So I draw a 2 by 3 area model. Remember that the x squared counts as sort of a 1x squared. 2 times 1 is 2, and x times x squared turns into x to the third power. 2 times 3 is 6. X times x is x squared. And finally, 2x times negative 2 is negative 4x. Then in the bottom left, 1x squared times negative 1. That is negative 1x squared. Negative 1 times 3x is negative 3x. And finally, negative 1 times negative 2 is positive 2. Now, once again, I can list all of these out and then combine my like terms, but I do want to show you that there's something interesting about the like terms. They typically, not always, but typically, align with one another on diagonals in our area models. See how these first two that I highlighted have x squared, and then the next two just have x's? So if I keep that in mind, I can actually start to write out the solution. Instead of writing out all the terms and combining them, I can kind of combine these steps. And I see that I only have one x cubed term, that's 2x cubed. Then I have a minus 1 and a positive 6x squared. That makes a total of positive 5. Then both of my x terms are negative. Negative 3x, negative 4x. That combines to make negative 7x. Remember that we're just sort of adding these terms together. We're not multiplying negatives times negatives, so nothing turns into a positive in this particular case. But we just get a larger negative value. And then finally, our constant is plus 2. So we combine like terms after we use the area model to assist us. So a couple of reminders. When you're multiplying polynomials, we can use an area model to help us organize the individual products, those little pieces along the way. Remember that multiplying terms that have the same variable will change the exponent. This means when you have x's times x squared, that doesn't stay x squared, that turns into x cubed. Remember that x squared means x times x. So if I multiply that by another x, that's obviously why we end up with x cubed. There are 3 factors there. And to simplify at the end, we always make sure that we combine our like terms. Now, follow up. Is it possible to use an area model and help us to do the sort of opposite operation? Can we divide this way? This is going to be something we see later in the semester at a more complex level. But starting off at a really basic level, if we were to try to divide, since that's the opposite of multiplication, then we use the area model just in the opposite way. Instead of us finding the inside from two things given to us on the outside, this time we can start with the inside and identify one of the two outside parts of the expression. Let me show you what I mean. Notice that in this top expression, we have 6x cubed plus 9x squared minus 12x all over 3x. That means we're dividing by 3x. The top divided by the bottom, the 3x. So we put the top part inside of an area model in one big row. So we have 9x cubed, 9x squared, minus 12x. I think I said that correct. Maybe I said 9x cubed. So 6x cubed, 9x squared, and minus 12x. And then we take our monomial, the single term that's on the bottom that we're dividing by, we write that in front. And now we sort of work backwards. Can we figure out what could go on the top? If we multiply by 3x, it would get 6x cubed. Well, 3 times 2 makes 6. And x times 2 more factors of x times x squared would make x cubed. Okay. Then in the middle, 3 times what? 3 times 3 would make 9. And x times x would make x squared. And then finally, 3 times negative 4 makes negative 12. And I don't need to put another x up top because I already have an x in front. So when we divide 6x cubed plus 9x squared minus 12x, our quotient, the answer when we divide, is 2x squared plus 3x minus 4. One more. Can we do the same process here? Can we divide the polynomial 6x cubed minus 4x squared plus 8x by the monomial 2x? Once again, if I'm dividing, I start with the inside and I work to the outside. So these three terms could go inside of a single row, dividing by 2x. 6 divided by 2 is 3. And x cubed divided by an x would give me x squared. Okay, so again, I kind of talked through that like I was dividing the inside, but you can also think of it as a multiplication and just figure out what do you need to multiply by. 2 times negative 2 makes negative 4. X times x makes x squared. And finally, 2 times 4 would be 8. And we don't need another x because there's already an x in front. So when we divide this one, we end up with 3x squared minus 2x plus 4. So wrapping up our notes on dividing by a monomial. So when we need to divide, we also use an area model to help us organize the individual quotients, those individual pieces across the top. Again, the process is sort of backwards, where we start with the inside and work to find the outside at the top. But then as far as vocabulary goes, this is the same process we could use to factor the original quotient by the monomial, or to factor it by a greatest common factor, a GCF. Either way, we're doing the same process where we start with the inside, we put a term on the outside at the front that we want to divide by, and then the quotient goes across the top to help us figure out what the result would be when we divide. Now you're going to move on to how do we apply these in a contextual situation. So the problem we're given to apply this says that a rectangular garden has a length and width expressed as polynomials in terms of x. The length of the garden is 3x squared plus 5x minus 2 meters, and the width of the garden is 2x squared minus x plus 4 meters. Now you may recognize these were actually the same dimensions of a rectangular garden we were given in our adding and subtracting video. And in that one, we were asked to find the perimeter from the length and width. Well, now we're asked to find the area. That's the space inside. And to figure that out, area is just length times width. So obviously the area of a rectangle being length times width as our basic formula, What makes this problem a little different is that our length and our width are both polynomials. So we just have to be able to multiply polynomials. And if we can do that and simplify, we will have the area. So let's show our work for this. The length is a trinomial of degree 2, and the width is also a trinomial of degree 2. So this is going to actually be a rather large box. This is going to be a 3 by 3. We've been doing a lot of 2 by 3s. So I want to make a 3 by 3 this time. We'll do 2 boxes there, or excuse me, 2 rows there, add another one underneath, something like this. So our 2 dimensions, and the order in which you multiply them does not matter. So you can put either dimension in the front, either one on the top. And we set it up like so. We have our 2 dimensions, and now the area is going to be what we get when we multiply and then combine all of our like terms. So we're going to start, I like to start in the top left and just work across each row till we get to the bottom right. So 3x squared times 2x squared. 3 times 2 makes 6. X squared times another x squared, that's a total of 4 x factors, so x to the 4th. 3x squared times negative x, that's basically negative 1x. When we multiply 3 times negative 1, that's negative 3. X squared times another x is x cubed. 3x squared times 4 makes 12x squared. Notice there's not another x, so the exponent stays a 2 here because we were just multiplying by a constant. Now in the middle on the left, 2 times 5 is 10. X times x squared is x to the power of 3. 5x times negative 1x is negative 5x squared, because there's an x times an x. And finally on the right, 5x times 4. 5 times 4 makes 20. And then we just have a single factor of x. Bottom left, 2 times negative 2 is negative 4. X squared stays just x squared because the bottom left number we're multiplying by, negative 2, does not have an x. Negative 2 times negative 1x, when we do a negative times a negative, that makes a positive. So this is positive 2 with a single x factor. And finally, 4 times negative 2, that's going to make negative 8. So time to write this out is a single expression. I'm going to combine my like terms. I see like terms there because they both have x cubes. I see 3 like terms here on this diagonal because they all have x squared. And I also see x's here and here, 20x and 2x. So I'm going to combine these like terms, starting with my largest exponent, 6x to the power of 4. Then in the red highlighted area, 10 take away 3 leaves positive 7, x cubed. I have a negative 4 and a negative 5 for my x squareds. That makes negative 9. And then a positive 12. And negative 9 plus 12, that's similar to 12 minus 9, which is positive 3x squared. 20x and 2x makes 22x. And then finally, my constant that would go at the end of my expression, I kind of ran out of room there, would be a minus 8. So 6x to the power of 4 plus 7x cubed plus 3x squared plus 22x minus 8. That would be the area of this garden. So we've seen how the area model helps us to multiply the different parts of our polynomials. We've also seen that we can work backwards, do the inverse operation and divide. If we have a monomial that we are dividing or trying to factor out, we can just write that in the front, and the original problem can go inside a single row, and we can determine what the answer is when we divide by putting the quotient of each particular box across the top. And finally, we just saw how we can apply these ideas to a contextual problem, sort of like this area problem we just saw here. Anytime we need to multiply two polynomials, we can set that up with an area model and multiply. So if you'd like a couple challenge problems, here they are. Show me what you got with finding the product of a cubic trinomial multiplied by a quadratic trinomial. This would be a challenge problem with a degree 3 and a degree 4, each of which are trinomials, so this will be another 3 by 3 box. But you pick what the coefficients and or constants would be. And finally, The second one, can you create a cubic trinomial where each coefficient is an even number and there's no constant? So every term should have a variable. And then divide whatever your cubic trinomial is by 2x and tell me what the answer would be. If you can do both of those, work those out on some paper, turn those in for some extra credit points. And good luck on these challenges.